Hi, this is Don. I had a request from a couple of y'all to go over how to use Solver to solve linear optimization problems. So I thought I would take one of the homework problems and go through a way to approach it that I think is logical. This is the Chapter 13, Problem 5, and we're talking about the land developer that wants to build condominiums. They've got a 40.625 acre site. The restrictions, the zoning restrictions, only allow 8 units per acre. That's the density control that's common in zoning. And they can build 3 types of condominiums, a 1, 2, or 3 bedroom unit with cost of $450, $600, and $750,000 respectively. They tell us that the units generate a 10% profit. So that tells me that if I build a $450,000 unit, I will generate 10% or 45,000 profit. So it's just saying that the more money I spend on units, the more profit I'm going to make. They say they have a budget of $180 million, and their experience tells them that they need to have a certain mixture of 1, 2, and 3 bedrooms, 15% 1 bedroom, 25% 2 bedroom, and 25% 3 bedroom. So that's what we're given in the problem. We're asked to develop a linear optimization model, and we want to come up with a optimal solution. There's some key words here if you're paying attention, and I hope you are when it comes to exam time. This is a linear optimization problem. It's not a integer optimization problem. And that's a key difference that I'll show you in a few minutes. And the last part of the question is, in essence, if we can increase the budget, what does that do for our profits? That's the way I interpret that. So let's look at a setup. Go to another sheet here. There's our problem again. And the way I looked at this, we have to identify, first of all, the objective function. I start with that. I know the text says starts with your decision variables, but mine works a little bit different. I want to know what it is that I'm trying to maximize or minimize, which you're always trying to do in a linear optimization problem. And in this case, the thing that jumps out at me is I want to maximize my profit. And how do I do that? Well, profit, as I said earlier, is 10% of the cost. So I can think of the profit as 10% of the number of the 1 bedrooms, type 1s, times their cost of $450, plus the number of type 2s, the 2 bedrooms, times their cost of $600,000, and the number of type 3 times their cost of $750,000. So my profit is 10% of the cost, and I want to maximize that profit. So the way I would approach it, I'm going to let X1 be my first decision variable, and that's the number of the type 1, the 1 bedrooms, X2, the 2 bedrooms, X3, the number of 3 bedrooms. So if we state our objective function as a mathematical expression, I would say I want to maximize profit, and that's equal to 10% of the cost, and that's the number of type 1s times 450 plus the number of type 2s times 600 plus the number of type 3s times 750,000. So that's pretty logical. Maximize profit, and that is our objective function. Now I want to decide on my decision variables. Well, the things that I can control are the number of each type of units. So those are our decision variables, and those are what we will vary in the solver solution. And I'll show you that on the next tab. Finally, we need to come up with the constraints. What limitations are imposed on this developer. Well, the first thing, we can't spend more than a budget. And we can state that constraint mathematically as the total cost is equal to the number of type 1s times 450, 2s times 600, 3s times 750,000. That total cost has got to be less than or equal to the budget of $180 million. That's the budget stated in the problem. Second restriction is the zoning restriction. We've got 40 acres, and we can have a maximum of 8 units per acre. That means the total number of units is equal to 8 times 40.625 acres. And for my mind, it works better if I rearrange that and I say that the total number of units divided by 8 has got to be less than that 40.625 acres. Okay, the next constraint is that the one bedrooms, the type 1s, must be 15% of the total. And showing that as a mathematical expression, x1, the number of one bedrooms, divided by the total number of condo units, x1 plus x2 plus x3, it's got to be greater than or equal to 0.15 or 15%. Similarly, 25% of the units must be two-bedroom, type 2 or x2. And mathematically, that's x2 divided by the total number of units, x1 plus x2 plus x3, greater than 0.25. The final restriction that I get out of reading this is that 25% of the must be three bedrooms. So that's x3 divided by the total. It's got to be greater than 0.25. So those are our constraints. One thing that you need to know when you're building a model is that the more constraints you add, the more difficult it becomes to maximize a profit or minimize a cost, if that's what your objective function is. In essence, if I added a sixth constraint here, more than likely my objective function, the maximized profit, is going to be lower than if I run it with just these 5 constraints. And that becomes important when we talk about integers in just a second. So here's my setup. Now let's actually put that into an Excel model, and I try to be as simple as I can, but make it obvious to someone that's looking at my model what I did. And I said over here in this first column, this is my objective function, the first part of the spreadsheet. My 3 decision variables, x1, x2, and x3. I've got the number of each of those types there, and then I created the total, of course, of those 3 numbers. I've got the cost of each unit, which we were given, 450,000, 600,000, 750,000. Total cost is just the number of units times the unit cost. And then I sum those up to get a total cost. And the profit is just 10% of this cost. Total profit is the sum of the profits on each of the units. And of course, mathematically, 10% of the sum of these is equal to 10% of that total. It works either way. So you could set it up either way. I just put 1 in here just so my model would be fleshed out. And I want to make sure. One thing I want to remind you of when you're doing Excel, I like to have my spreadsheet set up that it will automatically calculate. So whenever I change something, everything downstream changes. And the reason to my mindset is I don't want to change something and then think that my bottom line is correcting or adjusting. It won't do that if you're set to manual recalculation. And the way you control that, go to, I think it's formulas. There it is, calculations, options, and I click on automatic. By default, Excel seems to want to set it to manual so that you have to manually recalculate. And like I said, I don't like to do that, so I always double check to make sure it's set to automatically recalculate when any cell is changed. Okay, so now we've got the model set up. I put down here my constraints. And the reason I do this, I think I've said it in one other example I gave you all, was that when you start adjusting or playing around with a model, you may want to go back and adjust some of these constraints. We may want to change the budget, and I can see right there, you can see I was playing around that. Our budget is 180 million. Whoops, put another zero on that. So that's our budget, 180 million. And our constraints of 15%, 25%, and 25%. Total acres, now for this problem, that's not going to change, 40.625. And the zoning restrictions won't change. But I just get in the habit of doing that because in other situations you might be able to go back and play around with these various decision variables or variables that impact the decision variables and come up with a different solution by having those constraints changed. So let's go into Solver. We click on Data, Solver, and bring up our dialog box. And I've already got it set up just to save time. I hope you know now about how to add constraints. Click on Add and then type in your constraint. And I will demonstrate that just for the heck of it. Our objective function, click in there, and I want to maximize profit. Click on total profit and maximize that. My decision variables are, and I'll just change that just to show you again. Decision variables are the number of units. Just highlight those and it puts those in there. And then the constraints are the 5 that we talked about. And the first constraint is that B3, which is the total number of units. Okay, I confused myself because I forgot that even though I use a certain sequence when I'm constructing my constraints in here, once you say okay, it alphabetizes according to the cell designations over here. So you can see that B3 is first, B4, B5, B6, D6. That's not the sequence in which I build the constraints. I forgot about it rearranging those. So let's just go through the way that they're here. B3, go to B3, which is the number of type 1, is equal to B10. B10 is 15% times B6, which is the total number of units. 15% of the total number of units have got to be type 1. The next one is B4, which is number of type 2s, is equal to B11, which is the 25%, times the total number of units, 0.25 times that cell. The next constraint is for the 3 bedrooms. B5 has got to be greater than or equal to B12, which the 3 bedrooms have to be 25% of the total B6. The fourth constraint is B6 has got to be less than B13. B6, which is the total number of units, has got to be less than or equal to B13, which is the total number of acres, times B14, which is the number of units per acre. So that gives us the total number, the maximum total number of units, and the total we build has got to be less than or equal to that. The last constraint is D6, which is our total cost, has got to be less than or equal to B9, which is our budget. So those are our 5 constraints. All right, we're set up now, and we're going to run this using our basic constraints. Just click on Solve. And we finally get the dialog box that says we have a solution. I'm going to select to get an additional report that will be useful in solving the problem. So I'm going to click on Sensitivity and click OK. And it will generate a sensitivity report that I'll show you in a second. But let's look at what we came up with. But because we didn't restrict our decision variables to integer values, we get these fractional units, 40, 67, and 161, almost 162. Now, obviously, if you're building a condominium that costs $450,000, you're not going to build half a unit. If this were, an assembly line and these were in cents and pennies, then it becomes less significant that these are not integers, and you can would have to round them when you present the results to your management team. We would tell them we would build 40 units, 67 units, and 162 units, obviously, and that would have an impact on the actual profit. And you can actually run those numbers and see what the profit would become once you convert those into the round them up or down to integers. So you may ask, well, why don't we just constrain them to be integers to begin with? Well, remember I said if you add an additional constraint, then your objective function value is going to be impacted almost always negatively. That means that all things being equal, if I wasn't constrained over here by budget, my profit would be less. But let's just say if I'm going to go back to Data, Solver, bring up the dialog, and let's add that additional constraint, and we want to say that our decision variables, and the way we make them integers is click on the little down area, it says int, and it says that those three decision variables have to be integers. Click OK, and we get our screen, and you can see again it's alphabetized things. Let's put the integer up there because it's B3, even though that was the last constraint that I entered. And I'm not sure if I mentioned that when we're running Solver, we need to make sure we're using the simplex method as opposed to the default linear nonlinear. We're doing a linear programming optimization, so use the linear programming method, simplex. I always use this checkbox of make any unconstrained variables non-negative. And in real world problems, it's rare that one of your decision variables can be negative. Well, one way you could do that would be to add a constraint here to make these three decision variables, those cells, to be non-negative. Just be that they're greater than 0. But that adds another constraint, which, and as I said, the more constraints you add, the smaller and smaller, in our case, since we're trying to maximize, our profit's going to be. Let's run this with these 6 constraints. And we got a solution using integers, but it's different than the solution we got when we let Solver use an exact solution. We're forcing Solver to look for some combination of integers that will, in this case, maximize profit. And it just happens, because of the way this project is set up, that it gets an exact solution with integers here. That will not always be the case. So you're saying, well, why not use integers? It's given us a value, and why are these wrong? Well, we're wrong because of the technique. It's true that you could tell your managers, let's build 41, 83, and 149, and it will give us the maximum, the same $18 million profit. And that's true. But technically, and remember we're in academics right now, we're trying to run linear programming and not integer programming. Linear we'll be doing in the next module. And so there is a difference there. And I will show you. I want to click OK. And if you recall, the second part of this problem said, well, what if we can increase the budget? Well, can we get more profit out of this situation? In other words, we're going to say if we change this constraint, can we get more profit? Well, we don't know from just until we start playing with this how much we can change the budget before we have another constraint start to control the model. But at some point, if we put $1 trillion in here or $1 billion in there, one of these other constraints is going to control the solution. We can tell what that is by looking at the sensitivity report that I said we could run, and I did. And this is, remember, this is done using the non-integer solutions, and it shows a lot of information here about the decision variables up here. That's the solution. And down at the bottom, we're looking at our constraints, and we want to know if we change this budget, the total cost, will we be able to get more profit? And this sensitivity report tells us that if we can increase the budget by this allowable amount of it's like 36,937,500, almost $37 million, we can get more profit out of this. It means that one of the other constraints will control. And you can see up here that we've got some allowable increases for those as well. So let's just go back to our model. And I'm going to leave it set for integer right now. Let's just say the bank is very kind, and they say you guys can have $250 million budget. I don't know if we can use all that, but it's nice to know the bank trusts us that much. We'll run the model again, solver. I'm going to leave it set with the integer value, and we're going to solve. And it gets us a solution, and you can see that we didn't use up all of our budget. We only used up 216 million of the 250 the bank said we could spend. And so our profit went from 18 million to 21,675,000. That's roughly a $3.6 million increase. And if you remember, we said that we could increase our budget by 36 million, and that just happens to be 180 plus 36 gives you 216. So as I said, once we hit that value there, the maximum that the budget being increased helps us, all of a sudden we have another constraint controlling, and that's the total number of units. We hit 325, we cannot build any more units. So it controls. So why not use the integer result? Well, as I said, we added that constraint, and it will impact our objective function, which is the total profit. Let's see if I can copy this. And I want to paste value. I just want to remember what this integer profit was. F-I-T, if I could spell, of 21,675,000. So let's see if that holds true. Let's go back to data, solver, and I'm going to remove the integer constraint. We're back now to our original 5, and we still have our budget of 250. So let's solve it again using the non-exact solution. And in this case, our profit has gone up a little bit. For me, it's a lot of money. It goes up to 693,000. So that's what, $18,000 that it's increased. I would like to have 18,000 more dollars than you get with the integer solution. And even if you rounded these off and then extended out what the profit will be, I think you will find in this case that you still end up with more profit than the 21,675 you get with integers. So for our test purposes, when you're asked to do a linear programming, don't use integers as a constraint. and unless you're told to use integers as a constraint. So our solution in this case, again, says that we can build up to the 325 if we've got $217 million budget instead of the $180 million budget. And again, I would just tell my manager, let's build 49 one bedrooms, 81 two bedrooms, 195 three bedrooms, and you can extend that out and come up with your profit. And go ahead and try it, and you'll see that that's going to be more profit than the integer profit. Okay, hope that helps.